Okay, efficiency of full wave rectifier. So it is given by ratio of PDC by PAC, power delivered to the load divided by power given to the input of the transformer secondary. PDC is given by I square DC into RL, and PAC is given by I square RMS into RL plus RF plus RS. So after that, we just substitute the equations in the above formula. So we get I square RMS into RL plus RF plus RS. Again, the same assumption we have, RL is very high compared to RF plus RS. So from that we can write I square DC into RL by I square RMS into RL. So this RL will get cancelled. So for the remaining thing, so what is the formula for IDC? What is the formula for IDC?
2Im by pi.
2Im by pi. Substituted. Formula for I square RMS is Im by root 2 whole square. So Im will get cancelled. So the remaining thing you need to take. So it will be 8 by pi square. So how much you'll get? 8 by pi square. So you'll be getting around 0.812. So if you write the efficiency in terms of percentage, then it will be 81.2%. So the efficiency of full wave rectifier is 81.2%. And regulation formula is same, whatever we have studied. And again, form factor and transformer utilization factor, that is not there for the syllabus. So after this, the next one is PIV, peak inverse voltage. So what is peak inverse voltage? Anybody?
So, the maximum voltage that appears across the diode in reverse bias?
Yes, good. So it is the maximum voltage that a diode can withstand, or diode or a voltage that comes across the diode under reverse bias condition. So that is peak inverse voltage. So this is the maximum voltage a diode can withstand under reverse bias condition, or it is the maximum voltage that appears across the diode during the non-conducting condition, that is under reverse bias condition. See, in the last part, we had one diode. We had one diode, and it was having one reverse bias condition. I mean, one cycle has reverse bias condition. So we took it as VM. VM is the reverse voltage faced by diode 1 in half wave rectifier. But here we are having two diodes, right? D1 and D2. So in this we will be having two diodes which are going to face the reverse voltage each time. So that's why what we take is the voltage, reverse voltage, which is been appearing across diode D1 is Vm. The reverse voltage which is appearing across diode D2 is Vm. So total Vm PIV is Vm plus Vm, that is equal to 2 Vm. So since it is in opposite direction, it can be written as minus 2 Vm. So each diode is going to face a peak voltage in under reverse bias condition, or reverse voltage under reverse bias condition. So one diode is going to face Vm, other diode is going to face Vm. So total peak inverse voltage is 2 Vm. Okay, so this is 2 Vm. Since we are having two diodes here, we are going to take 2 Vm. So this is about the equations we are having. After this, there are the advantages. So there are very many advantages here. So let us first discuss about the advantages. Later on, we'll discuss about the disadvantages. So advantage here will be efficiency. We are having good efficiency, 81.2% efficiency we are having, and ripple factor is less, 48.2% is the ripple factor we are having. And one more thing is it is having only two diodes compared to, this is with respect to on comparing with respect to Bridgeway rectifier. In Bridgeway rectifier or bridge rectifier, we will be having four diodes. On comparing to that, it is using only two diodes. But coming to disadvantages, it's having high PIV, peak inverse voltages 2 VM. That means you need to select a diode which can withstand this much amount of reverse voltage. So automatically, when high PIV is required, then automatically the cost of the diode or uh, the uh, the diode manufacturing cost or the diode the feature should be high. So manufacturing cost will also be high. So the PIV is 2VN. That is one of the disadvantage here. And also we are using a center tap transformer. We are using center tap transformer. So first of all, by using center tap transformer, the cost will be high. So because of center tap transformer, the cost will go high because of center tap transformer is high compared to normal transformer. Along with that, we need a very exact tapping in the transformer. I was telling yesterday. So if you are having coils like this, so exactly at the center it has to be tapped, because number of turns here, this here should be equal to number of turns here. If there is a mismatch of one turn, there is a mismatch of one turn, then your output, instead of being like this, which with the same peak, you can see that they're having same peak. So what happens is, if there is a mismatch between the this coils and this coil, this has 50 turns of coil and this has some 52 turns of coil, then what happens is the output will be like this. You can see one is lower, one is higher. This kind of mismatch will come, and this will keep on continuing like this. So this disadvantage we are having. So tapping has to be done properly. If the center tapping is not done properly, then we are going to get a distorted output or a noisy output. These are the disadvantages we are having. So to avoid the center tap, next what we are going to do is, we are going to use the bridge rectifier. Okay, so bridge rectifier, it is called as bridge rectifier because it is going to use the concept of Wheatstone bridge. You have seen that in Wheatstone bridge, we are going to use resistors, PQRS resistors, and we are going to balance them and to find. So the same concept is applied here, but the thing is, instead of resistors, we are going to use diodes. That's why it is called as bridge rectifier. So here in the bridge rectifier, so we are going to use four diodes. Four diodes are being, sorry. This is the bridge circuit. These are all the terminal points. This is the secondary of the transformer. This is the primary of the transformer. This is our AC input signal. And we take the output across BD. Okay, this is the circuit we are having. So there are diodes, 4 diodes. We'll name it as D1, D2, D3, D4. So here the concept is, let us name this as K, this as L, and this is our input. For this bridge, this is the input. Even though this is the main input, since the voltage is stepped down, so this is our actual input which is supplied to the bridge circuit, and we take the output across RL. So the concept in bridge rectifier is, in one half cycle, if I take this as one complete cycle, in one half cycle, 2 diodes are going to conduct. In one half cycle, 2 diodes are going to conduct. If in this we are going to have D2, D2 and D4, in this we'll have D1 and D3 conducting. So when D2, D4 are conducting, D1, D3 will be off. When then D1, D3 is conducting, D2, D4 will be off. Okay, so that is what we are going to study here. So, and you can observe here, are we using any center tap?
No, sir.
We are not using center
No,
tap.
sir.
So automatically what happens? The cost gets reduced. See, for you should not tell that no, there is 4 diodes here. How the cost will be reduced? See, diode cost is very less when compared to transformer. The cost of diode is cheap, but transformer is costlier. So here, even though we use 4 diodes, the cost is less compared to that because we are not using center tap. Now let us try to analyze it. So let us plot the input signal. So let us consider this as input signal, and we'll try to plot the output. This is the output we are having. So when see, for current, to complete one cycle or one complete loop, what it needs a positive starting and negative ending, right? It will start from positive and end with negative. So it needs a closed path for flowing. So now when you take at this particular point, so during that time, so this will be positive, and again this will be at negative. This will be positive, this will be negative. Now even this also will be like this, 10 0 10 20 0 20, like that, but the middle terminal we are not going to use. So now what happens is, the entire voltage whatever you are applying will be 20 volts. It is not like 10 0 10, like this. What we are doing, we are considering, so 10 volt for one, 10 volt for others. I mean, other half cycle. We had studied like that in the previous circuit. But here, since we are not using center tap, it will be 10 to 10. So what is the total voltage applied now? 20 volt is the total voltage applied to the bridge circuit. But if I take a center tap, then it will be 10 volt. But here we are not taking center tap. So that's why 10 to 10, 20. If you are taking 20, 20, then it will be 40 volt. Okay, please remember this. This is the only change we are having with respect to transformer from center tap to this. Now, so during first here we get a positive cycle and here we will be getting negative cycle. When you get positive cycle, what happens? The current starts flowing like this. So when it comes to this point, when it comes, the current comes to this point, there are two paths for the current. It can go like this and it can go like this. Okay. So now when the current goes like this, what happens to diode D1?
Closes. It opens.
Open. So it becomes open. Okay. Now what happens to the current here? Will it flow?
No, sir.
Huh? Will it flow through this?
Yes,
It
sir.
will flow.
Sir.
It will flow, right? Because it becomes forward bias. And again, it will come at this particular point. There are two parts, like this and like this. What happens to this? If the current flows here, what happens to D3?
Open. Okay.
Reverse
Open
bias,
circuits.
open circuit. So the only available path is this one. So current will appear across the load and it will come back like this. So this notch indicates that there is no contact between this wire and this wire. Now again, it will come here. And again at this particular point, there are two paths. One is like this, one is like this. Here it cannot, can the current flow like this? Can the current flow like this? See here it has two paths. One, the current can flow like this or in this direction. So can the current flow from D to A? My question is
No, sir.
no, because it is already
Open.
open circuited. Open, we cannot. So the current can only flow through this diode. And then again it will come here. Now can the current flow like this
No,
from
sir.
C to
No, sir.
B?
No, sir.
No,
No,
sir.
sir.
So the only path available is this one. It will come here. So since this is positive, this is negative, this is negative. Now what happens? The current completes one complete loop. See, it started here, it went on like this, it came to the resistor, this diode, and it closed the loop. So one loop is completed. So because of that, we will be able to find some voltage across the output. Okay. Now, in the next half cycle, now what happens? This will be getting negative half cycle, this will be getting positive half cycle. So the secondary of the transformer is designed in such a way that it will be changing the phase. First half, if positive here means negative will be here. If negative is given here, positive will be given here. Okay. So now what happens is here, now the current will start flowing from this end. So the current comes here, and this when the current comes here, there are two paths. One is to go through this diode, and other one is to go through this diode. So now, if it tries to go here, what happens to this diode? This one. Hmm?
Act like open, sir.
Open circuit. That is, it becomes reverse biased. The current can flow like this, and again it comes here. Can the current flow back like this?
No, sir.
No. So it becomes reverse bias. So this is also open. Now the only path available is this one. It goes to the load resistance and again it will come back here. So now it has to go here and here. Now here at this point the current can go like this.
No, sir.
No,
No.
sir.
So the only available path is this one. So it will come back to K. See, it started from L, it stopped at K. If it starts from K, it will end at L. So when this is positive, this will act as negative. When this is positive, this will act as negative. So this is how it is going to complete the cycle and we are going to get the output. You can observe that during first positive half cycle, we will be having D2, D4 forward bias. In next cycle, next half cycle, we will have D1, D3 forward biased and D2, D4 reverse biased. In this way, the bridge rectifier is going to work. Okay, so this you have to explain how it works and all. After that, we are having the advantages, disadvantages. So what is the main advantage here?
Fast is reduced.
Center tap,
No use of sentry tap.
center tap transformer is not used. Not use the center tap. So cost is less. And also here coming to PIV, peak inverse voltage. Don't get confused. See, in half wave rectifier, I told PIV is VM. In full wave rectifier with center tap, I told PIV is 2 VM. Don't write it is 4 VM in this case. Okay, why? Because here, since in one, let me know, in one half cycle, how many diodes are going to conduct?
Two, sir.
Two diodes are going to conduct, right? So when two diodes are going to conduct, here what happens is the VM is going to be shared among each other. It becomes lesser. It becomes lesser. Instead of VM being offered to diode D1, VM offered to diode D2. Here, since both of them are facing same voltage, what happens is VM becomes VM by 2. So VM by 2 in one half cycle, we'll be having only half VM. Next, D3 and D4, both of them are going to face voltage, reverse voltage VM. So half of it will be faced by this and half of it will be faced by this. So now what is the peak inverse voltage at the diode, each diode? Hmm? At each diode, what is the peak inverse voltage?
VM by 4.
VM by 2.
VM by 2 at each level. So if you take VM by 2 for one cycle, one half cycle, and VM by 2 for the other cycle, then totally we'll be having only VM, right? I repeat it again, don't get confused. See, in one cycle, in one half cycle, in our earlier years, one half cycle, that reverse voltage, whatever we give, that has to be faced by one diode. That say VM has to be faced, or that reverse voltage VM will be appearing across the diode in one half cycle for a single diode. But here, since we are having two diodes, the same VM is appearing. But how many diodes are facing that? Two diodes. Two diodes are facing that reverse voltage. When two diodes are facing that reverse voltage, what happens? It gets splitted up. Both of them are going to share it. Okay. So now what happens? Instead of being Vm, it becomes half of the Vm. So in the same way, so now we can tell in one half cycle, diode, the peak inverse voltage faced by the diode is Vm by 2. So for two half cycles, it will be Vm by 2 plus Vm by 2. Total it is Vm. Okay. This is why we are having Vm, not 4 Vm. Don't write like that. I see. Simply they'll think Vm or Vm for one diode Vm, 4 diode 4 Vm, 2 diode 2 Vm. It is not like that. Okay, two diodes are going to face the reverse voltage equally in one cycle, one half cycle. So we are having the peak inverse voltage gets reduced. Okay, so PIV of the diode is Vm. That means we can use a normal diode which is having low capability, low withstanding. That itself is sufficient. So you can use the diode becomes still cheaper. But when it comes to center tap full wave rectifier, we have to use 2 Vm. That means the diode which we are using should have higher capacity. So when you go for higher capacity, automatically the cost will go high. And since the center tap is not used, cost is less and transformer is not bulky. Coming to the disadvantages, here we have to use two extra diodes. We need to use two extra diodes, and also since we are going to use and we can tell the circuit becomes bulky because it uses 4 diodes. No? The circuit becomes bulky even though we avoid bulkiness with respect to the transformer, but because of this diode the bulkiness increases. And also since we need to have, we will be using 4 diodes. So regulation and efficiency is slightly poor compared to center tap full wave rectifier because all the diodes D1, D2, D3, D4, all of them should match. Matching in the sense, if this has a zero 0.7 volt drop, even this should also have 0.7, this should also have 0.7, this should also have 0.7. The characteristics of all these diodes has to match. If any one of the diode is having, let us say, this is having 0.4, this is having 0.8, during that time what happens now? The output peak will not be same. This is the output peak where you'll be having same level of output. But if you have this kind of variation, then one will be small, other one will be big, other one will be small, other one will be big, like this you'll be getting. So then it is of no use for us, and we have to do a lot of filtering process. And again, it will efficiency go slow. So since we are using 4 diodes here, the regulation and efficiency is slightly low because all of them has to match. So sometimes if it matches with voltage also, it might slightly deviate from in the current. So that's why we tell regulation and efficiency is slightly more compared to the full wave rectifier. Okay, this is about advantages and disadvantages. Now coming to derivations. See, derivations are same as full wave rectifier with center tap. That's why even in the textbook I have not given. Same derivations, whatever you are having for full wave rectifier with center tap, the same derivation, same equation you have to write for bridge rectifier. The only change what you will be doing is there are only two changes. That changes are wherever you are having RF, anyhow RF you are going to ignore. RF, there you need to write 2 RF. There you need to write 2 RF, and the PIV. PIV is VM. These are the only two changes you need to do. Okay, rest of the things are same as it is. Everything is same. So there is no change in any uh, equations. All the equations are same to same. Only in the place of RF, you put it as 2RF. In the place of in the PIB, you'll be doing PM. Not only in my textbook, in any textbook, they'll not give you bridge rectifier derivations because derivations are same to same only. The same equations you will be writing here. The only change is RF. What is RF? What is RF?
The forward resistance.
Why it is 2 RF here?
Because two diodes are used and
Hmm.
there'll be forward resistance with two diodes in each case.
Yes, good. So in one half cycle, two diodes get forward biased. So the two diodes forward resistance is taken into consideration. That's why it is 2 RF. This is about the rectifier. So before going on to the next topic, let us do some problems and we'll go for filters. If in a few filters also, it is the just the next version of rectifier. The same circuit will be having, but one capacitor and inductor we are going to add such that it is going to filter out the unwanted signal. So how we are going to filter it out? Let us see it later. So whatever the problems which have given in the textbook, it just go through that. It is more than sufficient. No need of searching too many things. So it is sufficient. So let me take uh, problem. Okay. Page number 39, example 2.9. Example 2.9. The full wave rectifier supplier power, the full wave rectifier supplier power is 3 kilo ohm load. So 3 kilo ohm, make it 4 kilo ohm. I'm changing it. They are telling it is 4 kilo ohm load. The AC voltage applied to the diode is, take it as 190, 0, 190 volt. If diode resistance is 10, let it be 10. So find the average load current. Average load current means IDC. Average load voltage means VDC. RMS value of ripple voltage. RMS value of ripple voltage. They are asking. Ripple voltage. And D, rectification efficiency. Okay. So whenever they give you like 190, 0, 190, like this, please remember this is given in RMS. This is given in RMS. Whenever they tell you 190, 0, 190, 40, 0, 40, like this, whenever they give you, remember it is VRMS. So if you want IDC, what is the formula for IDC? What is the formula?
2 im by pi.
2 im by pi. So to this is in VRMS, we need to get im to find IDC. But IM cannot be found directly. So what we need to do? We need to find VM. So what is the relationship between VM and VRMS? VRMS is equal to VM by root 2. So this we can write it as VM is equal to root 2 into VRMS. So VRMS means 190 is your VRMS value. This is the transformer value with the center tap. See here it will be having 190. Here it will have 0. Here it will have 190. Okay. So any one value you can take because both are same. So root 2 into 190. That gives you VM. So tell me the answer.
Two 268.7.
268.70.
268.70 volt. Now, how we can find out IM now? IM is equal to VM by RL plus RF. Why I didn't take RS? Why I didn't take RS?
So they didn't give, sir.
Yeah, they didn't give, so ignore it. Okay, now so substitute and tell me.
Six 6.71.
6.71 ampere.
No, so milliampere. Ampere
Milliampere.
0.067, sir.
Milliampere.
6.7 milliampere. So substitute it here and tell me the answer for IDC. 2 into 6.71 into 10 to the power of minus 3 by pi.
Sir, it's 67 milliamperes.
67.
Milliamperes.
Okay, 67.1.
So
67.
it is 42.65 milliamperes.
42.65 milliamps. All of you got the same?
Yes, sir.
Yes, sir.
Sir,
Yes, sir.
42.67.
Okay.
Yes, sir.
Yeah, fine. No problem. And now next we need to find VDC. So VDC is equal to IDC into RL. You can do. Or you can also use 2VM by 5. Anything you can use.
Sir, 170.6.
How much?
170.6, sir.
Okay. Next is RMS value of ripple. How we can find this RMS value? So we have formula for ripple. What is the formula we are having?
IAC by IDC.
R is equal to, we can write it as RMS value. You just go to the ripple factor derivation. RMS value of ripple voltage. Ripple voltage nothing but our AC voltage. Ripple means that one, variation we are having by value of DC component. So R is not known, but when R is not known, we can take our standard value. What is the standard value for R? Yeah, 0.48, because 48.2% is our ripple factor for full wave rectifier. So 0.48. So RMS value we need to find. RMS value of ripple voltage. And you cannot take this RMS because they are asking ripple voltage. Ripple voltage means how much voltage your AC voltage you are having at the output side. What about this VRMS? What is this RMS VRMS? What kind of VRMS is it? It is the RMS value of the voltage which is available across the transformer secondary. But what about this RMS value? It is the RMS value of the voltage which is available across the resistor, across the load resistor. Okay. Now you cross multiply this VDC into 0.48. How much you'll get?
So 81.88.
81.88 volt. So that is the RMS value. Now last is efficiency. PDC by PAC into 100. So therefore that I square DC into RL by I square RMS into RL plus RS. Yeah, first you can tell me.
So 80.8%.
How much?
80.8%.
Okay, 80.8%. It is okay. It is in within the limits. We have got 81%. It is within the limits. It should not cross. Suppose if you are getting some 83%, then it is wrong because it is greater than our theoretical value. Okay, so that is about this one. So we'll continue the rest in the next class.